Hello, everybody. Hi. What else can happen? I don't know. I was driving here. I don't know if you hear the news. My airbag exploded in my face. It wasn't nice at all. So if I faint or something, you know, that's the problem. Not only that, I wish I could have subtitles. If I say something is weird, just ask me. If I freeze thinking of a word or make up something, it's just because I'm Italian, so that can happen. Happens, right? So you read this, guys. Emanuele Tozzato. Currently, I'm writing Ruby code at Sony for PlayStation titles. So we support online functionalities for titles that Sony publishes internally or other studios. So I'm here to talk about Redis and to see how we are using it to help our database performances facing heavy-duty operations. So how many people here are using Redis or familiar with Redis or other key-value data store? Okay. So from Wikipedia, we know that Redis is an open source, network, in-memory, persistent, generalized key data store, meaning that it's a server that can be reached over the network. That's easy. And it keeps data store in memory, but it's also persistent right into to disk. And of course, it's a key value, or it's a key advanced data store, as is described in the documentation. It's a great tool. It has been really fastly developed in the last month, so it's almost hard to keep up with all the new features that are added all the time and the bug fixes. It's very popular in the community. It has a very rich and powerful set of data structures, and it's fast. It's very, very efficient. There is almost no difference between writing and reading. So it fits well for our purpose. I was going to show 2 applications tonight, but I will limit to 1 because the presentation became pretty long. So in this case, we'll see something about large collection of MySQL entries that need to be sorted and ranked. So rank is something that it's important, especially for video games. So that's how this was a big problem for us. And it's the relationship of items that belongs to a set where the first is equally ranked or highly or lowly ranked to the second for each couple. For example, a game leaderboard is something that we do every day, or a products table could benefit of this solution. Okay, so this is the example of the simplest ever game leaderboard, or a high score ranking table. It's a place where, associated to a player, there is a collection of achievements that are usually identified by a score and minimally by a timestamp at least. On a structure like that, it's easy and very direct to retrieve a score, of course. When we want to know the rank, so the position of this leaderboard entry for the player, it may get a little bit complicated or intense for calculation. Because basically, I need to know how many people have a bigger or a smaller score compared to mine. But it's not always so easy and linear. In the theory of ranking, there are different approaches to how you can or want to manage entries that have the same value, the same score. So 5 examples here are ordinal, where no matter what the score, the tie score is, you decide to rank those items according to a second criteria. So this is vastly used even in video games. For example, I have the same point, and I am penalized because the second criteria is alphabetical, for example, on the username. I've seen that. Or maybe the second criteria is a timestamp. So the first person that achieves a level is considered higher or better than someone else that repeats that later. Another way is to keep a fractional score. We can have dense ranking, which is often required for games. So all the players rank the same. And then we have modification of this dense ranking called standard, where basically every tie position occupies the next place or the previous place, not making that available or making that unavailable for other items in the set. This is the same simple table, and we have scores, player, and the timestamp, and those are representation of the ranking for those players according to the different criteria decided. Calculate the rank with SQL is not difficult. There are different approaches, of course, according to what criteria someone wants to achieve. That's an example of dense ranking using variables, which is not too hard on the database. Often, though, the complexity of this calculation goes up, especially if you are using pagination. So you only have a subset of entries to calculate rank that is not linear but is dense. You need to do a full table scan and calculation on all the items that you want to calculate. That was a repetition. OK, so this will be an idea of real-time ranking, the queries that we just saw. And why is that a bad idea? I just said that. Huge complexity calculation, even with big indexes. And of course, to make it more complicated, huge sets yield a higher number of tie items or entries. That's not good. The first solution everybody comes up with is a pre-calculated ranking. So you can decide which column or which columns are subject to ranking. And every time there is a modification database, you can apply your algorithm, your background jobs that run, and calculate the rank and assign the rank to every leaderboard entry. But we quickly discovered this is not a feasible solution. It's not optimized at all, especially switching from Oracle to MySQL. Huge table locking, and the number of calculation gets really high because every time a leaderboard entry is changed, all the leaderboards need to be updated. So if you're ranking many columns, you have to do a calculation for every column, for every player that is ranked for each event that changes the ranking order or the leaderboard. And if we are talking on a medium video game that has 500,000 players that can be playing simultaneously like 1,000 games, that's a problem. That's a problem. Database is almost impossible to keep up. It doesn't scale. This is an example that nobody can see of one of the leaderboards we use. Yeah, I didn't want to expose all the columns, so it's gray, but it's the whole page. We have, on the average, 150, 180 columns on a leaderboard according to different games. So complicated and hard. Any question? Good. So a good approach that a lot of people are beginning to follow is delegating to Redis part of this hard ranking job. The data structure that everybody uses, of course, is the sorted set that has an incredible implementation with a very, very low complexity. The maximum is log n plus m, where n is the size of the set and m is a subset of the information you want to know. And it can be flexible and very fast and reliable. It works well. That's it. Okay, let's see. On a sorted set, three things that we want to keep in mind that we start with are the concept of key, score, and member. The key is the name of the sorted set itself. The score is the value that Redis will use to keep the rank order, and member is what identified your entry. I wrote out some of the comments that we use most frequently. There are a few more, but let's see this. Everything that starts with Z is about the sorted set, and whenever you see rev in a parenthesis means that it's an optional part. There are two comments. There is a rev rank or rev range and a Z rev range to have the inverted order of the set. So with add, I add, of course, one member to the set, and that complexity is logarithmic. I can ask the number of members using the cardinality, and that's good for pagination calculation. I can ask the rank or the reverse rank of any member in the collection. So I have an instant rank for the entry. And that's complexity of 1. And then, more important, I have range and range by scores, which return a subset of the sorted set in different ways. The range will take start and stop, like first and last line, 0 index of the set. And the range by score combine a limitation, a minimum, a maximum score I'm interested in, and eventually a limit and an offset. We'll see that soon. Another optional param is WS, or with score, that will return a double list of members and their score if it's needed. We'll see why that could be needed or not. Any questions? Okay, so this is how Redis, in our case, starts to meet a leaderboard. So every time we create or update an entry in the leaderboard, we add to the sorted set the value at the column that we want to rank. And of course, every column we want to keep a track of will be added to the collection, to a separate collection, of course. So we'll be ranking column number 1 in this case. So column number 1 will have a value of 123 for the entry number 10, and we'll have a value of 145 for user 12, for example. And this will be done for all the columns independently. Yes? Uh, mhm. I never tried. I'm sure it's possible. The thing is that it's so fast that we never had any problem with that involves the use of protection. No. Yeah. It's very, very, very fast, losing fast. And after that command, the 4 commands, the expected result, of course, is asking what's the reverse range for column 1 from the beginning of the set to the end of the set. -1, it's the last items. And of course, we'll have 12 and 10, and 10 and 12 for the other column. And instantaneously, we'll have the rank for the 2 entries. Things get a little bit complicated as usual. In this case, for example, 2 columns, 2 entries for the column 1 have the same point. So a previous implementation of this, that's a little bit, that's okay. The previous implementation of a sorted set would follow the logic of first insert, highest ranking. So first achievement, consistent to what we were happy to do with the video games. But I'm not sure when that happened, but this last version uses a second criteria internally. So once the score is tied, Redis will resort the collection lexicographically or alphabetically using the member. So this is in response of what the last implementation of sorted set returns. This is one of our first takes, meaning that in case of tie, we will concatenate the timestamp or the reverse timestamp, depending on the default sorting order of the column we want to track. And this will be consistent with our idea of first achieved best ranking. But this is just an example that works with video games. Thanks.
Just real quick, as each score is updated, we see, I saw the add. What happens to the previous score?
Well, a double insertion of the same value, the same score, would return 0 and be not attached. A different score will be updated. So you add and update is an add on an existing set. So we just add everything, and Redis takes care of updating.
Is there any sort of C removed?
Yes. Yes, I didn't put it because I didn't have space, but there is remove by range, remove by score, or individual remove, of course. Okay, very quickly in quickly an introduction of some Ruby code to see how we implement it in real life. So our Redis leaderboard has 2 calls as an after save and after destroy hook that, of course, synchronize MySQL, the object, and Redis. So let's see. There is some configuration. Of course, we're not showing here. The class is a little bit more complicated, but the object itself, the class knows which columns, of course, we want to keep track of. So for every save or update, we'll go and make sure that the value changes, and that's because of our decision of concatenated timestamp and score. the first implementation we had didn't take into consideration the fact that the value, the score, was actually changed or not, and will just update all the columns, even if they were the same. But that will update the timestamp on the insertion. So a previous achievement not changed will be degraded, and we'll have to take care of that, of course. So if the value is changed, of course, I'll add the value, the score for that entry. So the self ID, of course, is the ID of the leaderboard, and I'll send the value to the appropriate key. The key is the name of the class, of the column. So I hope you can see this is the part where we actually find a leaderboard. I'm giving two examples using Z-range and Z-range by score. The params that this find leaderboard uses for fetching the leaderboards are similar to the classic that we use for pagination. So we have a per page and a page we want to fetch. And those two values, the two params, are enough for calculating start and stop, or the indexes that we want to fetch from Redis. And a part is missing where we do some boxing of those values, because we don't want to have a negative index by accident. But I just didn't need it to put it here. So once I have the first index and the last index, I can just invoke rev range or range according to the sorting order sorting param that I'm passing, and that will return an ID, an array of IDs of the leaderboards I want to fetch. I didn't mention we're using redis-RB and redis-object that we built on top of redis-RB, both on GitHub. For the second way of fetching the subset, I calculate the limit and the offset. It's more tolerant. Redis is more tolerant with limit and offset. You don't risk to have an out of bound in the indexes, and that I discovered with pain. So I will suggest to use that. And the syntax is the same. The result is always an array of IDs that, of course, Redis returns in the correct order of the rank. With those IDs, we go to MySQL. We just fetch the collection simply with no effort. And we loop through the array of IDs, because those are in the correct order. MySQL will never respect that order. And we assign the rank, which is an attribute, writable attribute on this class. And of course, since the collection of IDs is ordered, I can just loop through and assign confidentially the rank to each entry. Last, I sort that collection using the rank. And of course, I may use a param to reverse the order if it's needed. And in the end, I'll just create a will paginate collection for having those params that I used in the beginning to fetch the collection ready, page, and okay. Questions on that part? It's pretty simple, isn't it? Another big requirement of leaderboards is the so-called find around me. The situation of a find around me is myself, I have a rank, and I want to know where I am located in a leaderboard. And more precisely, usually, I want to be in the middle of the rest of the player when I visualize this collection. And also, this is super simple to achieve with Redis. So I'll have a number of padding number of items before and after me. We'll call it num above and below. And once I fetch my rank, which is a simple operation, as we just saw, it's available for every item in the collection. I can just calculate limit and offset around me, and again fetch by score around that player using reverse order if it's needed, and that's it. That's how easy and quick we can keep up with huge collection of high ranked score tables. This is a previous example. This is how the find around me query was running before introduction of Redis. And not only it was hard, like on 500,000 records, this is hard. It takes time. But it's also imprecise, because to break tie, condition can change. It was just a nightmare. I know. It was very quick. This was supposed to continue with Resque, but I thought it was too long, so I split into parts, and maybe I'll try to do it another time. Any question?
On your slide that shows sorting, if you have the list in a sorted rank from Redis, couldn't you just call all those records in MySQL via ID, and wouldn't you then get them back in the same order?
Yes, probably. We had some issues with sorting that collection directly with MySQL. I don't recall that, but we had to have that approach.
The vset returns in order.
Yes, right. Yes, that's in order. That's how we assign the rank.
So if you did a find by within an array of IDs, you should also get that data from MySQL
that's true.
in the same order. I would think.
Yeah, that should work. I'll get back to you. I'll find out.
So you added Redis for performance scalability. How many actual instances have you ended up using?
Different games, of course, different application use different set of Redis. We actually separated leaderboards, player presence, and other events on different servers. I think leaderboard, the main leaderboards are up with a single instance of Redis, 32 gigabyte of RAM, something like that. So not a small machine, of course, but totally doable. we'll know this when the next application will be in production, because things always work until you try it for real. In the real world, we don't have any game out that uses this technology yet. So we can just hope that it will be enough. The high traffic title is currently on Oracle, and we'll know the benchmark soon. Yeah, the testing is it's easy. I mean, we do load tests, but it's never enough for a real world. So we'll see.
So when would you use this instead of Memcached? Is there a size limit? I know Memcached has small sizes. It sounds like you do a lot of the same things.
Does Memcached has structures like that? I don't think so. No. Well, that's the reason why we're using this advanced data structure.
So it's mostly for the adaptation.
Oh yeah, we use Memcached when we have to expire content. There is an option of expiring things for Redis too, but we separate the two things. Thank you.